All right, so we looked at fluid force problems. That was the first part of section 8.3. The other part of 8.3 is moments, centers of mass, and then centroids. Okay, 8.3 is kind of big here. So like a lot of calc books actually split these two topics up into separate sections. But anyway, so this is like 8.3. But okay, so what if we want to look at the center of mass in a one-dimensional system? Methods for finding centers of mass or a balance point of an object are ultimately based on a well-known playground principle. Okay, if two people with masses m1 and m2 sit on opposite sides from the pivot point of a seesaw at distances d1 and d2, then the seesaw will balance if m1 times d1 equals m2 times d2. Okay, you got see figure 1 there. Now suppose that the seesaw lies along the x-axis with m1 at x1, m2 at x2, and the center of mass at x bar. Okay, d1 is x bar minus x1, and d2 is x2 minus x bar. So I've got a picture showing that description there. The playground principle now becomes m1 times d1 is x bar minus x1 equals m2 times d2 is x2 minus x bar. Okay, if you solve this equation for x bar, that makes the balance point of this two-dimensional system located at x bar, which is, again, I'm solving this equation here. X bar equals m1 times x1 plus m2 times x2 divided by m1 plus x2, or plus m2. Okay. In general, x bar is where you're taking each mass times the x value and then adding those all up, and then you're dividing by the total mass in the system. Okay. Now this notation right here, we're going to see this a lot in chapter 11 when we get to sequences and series. This is the summation sign. Okay. So I'm adding up, going from I equals 1 to n. I is the subscript here. M sub I times x sub I. So the subscript is changing each step. So when I plug in 1, m1 times x1 is the first term, plus plug in 2, m2 times x2 is the second term, plus etc. I'm ending at n. Okay, and here's a definition next. The quantities m1 x1, m2 x2, m3 x3, etc., all the way up to m sub n plus x sub n are called moments about the origin, or just called moments. The sum of the individual moments, capital M, is called the moment of the system about the origin. Okay? So that's terminology that you'll find in the book. Problem 1 here says find the moment, capital N, of the system about the origin and the center of mass, x bar. Okay? Well, to get the moment of the system, I'm taking each x value times the mass. Okay, so -2 times 25 plus 3 times 20 plus 7 times 10. And that gives me 80, it looks like. Okay, that'd be the moment of the system about the origin, is what we call it. Okay, and then the center of mass, x bar, is where I take the moment of the system about the origin divided by the total mass in the system. Okay, so if I take 25 plus 20, that's 45, plus 10 is 55. That's the denominator. 80 divided by 55, that's going to reduce. So 5 goes into these two numbers evenly. 5 times 16 is 80. 5 times 11 is 55. So 16 over 11, if I plot that point, 16 11ths, that's be bigger than 1. That point would be the point that balances the 3 points. In other words, is what we're saying. Okay, so let's extend this topic to 2 dimensions. Okay, by considering a system of n particles with masses m1, m2, m3, all the way up to m sub n, and it's located at the points x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3, all the way up to x sub n, y sub n. Okay, so I got n points here in the plane. Definition, next. The moment of the system about the y-axis, m sub y, is where I take each mass times the x value, so m1 times x1 plus m2 times x2 plus m3 times x3 plus etc. up to m sub n times x sub n. Now, take into account this is the moment of the system about the y-axis. Okay, so I'm using x, in the formula there. The moment of the system about the x-axis is m sub x, and that's where I take the mass times the y value. Okay, so m1 times y1 plus m2 times y2 plus m3 times y3 plus etc. up to m sub n plus y sub n. Little m is going to be the total mass in the system. Okay, and that's just notation that we'll be using here for going forward. Then the center of mass has coordinates x bar, y bar. That's going to be the point that would balance all these points. If I were to put them all on a scale. X bar is where I take the moment of the system about the y-axis divided by the total mass. And y bar is where I take the moment of the system about the x-axis divided by the total mass. Okay. Now, sometimes I see students will have these mixed up. Like they see y bar is, here's y, and this, x bar is goes with x. Don't do that. Don't do that. Okay, that will give you a wrong answer. So, let's see, problem 2. It says to find the moments in the center of mass of the system of objects that have masses 6, 3, 2, and 9 at the points, these points that are given there, respectively. Okay, so the first mass, 6, is going to be at the first point, 3, negative 2. The second mass, 3, is going to be at the second point, 0, 0. The third mass, 2, is going to be at the third point, negative 5, 3. And the fourth mass, 9, is going to be at the fourth point, 4, 2. So in other words, I'm looking for a point on the plane that's going to balance all 4 of these points, like if I were to put all 4 of them on a scale. Well, let's see, the total mass in the system, if I take 2 plus 3 plus 6 plus 9, I get 20. That's little m. The moment of the system of the y-axis is where I take each mass times the x values. Okay, so that's using this formula right here. Take the mass times each x values. Okay, so m sub y, I'm going to take 6, the first mass, times 3, and then plus 3 times 0, plus 2 times negative 5, plus 9 times 4. And when I add that up, I get 44 total. The moment of the system about the x-axis is where I take each mass times the y values. Okay, so I'm going to take 6 times negative 2, plus 3 times 0, plus 2 times 3, plus 9 times 2. And when I add up those numbers, I get 12. Okay, so then to get x bar, y bar, I take to get x bar, I take the moment of the system about the y-axis divided by the mass, and to get y bar, I take the moment of the system about the x-axis divided by the mass. Okay, so to get x bar, I take the moment of the system about the y-axis, that's 44, divided by the mass, that's 20. 44 divided by 20 reduces to 11/5. And then the moment of the system about, or excuse me, the value of y bar is where I take the moment of the system about the x-axis, 12, divided by the total mass. 12 divided by 20 reduces to 3/5. Okay, so this is my answer. The point, 11/5, 3/5. Now, it's a good idea to plot the point just to make sure that you're in the neighborhood of the graph, because if I get a point that's way out yonder, that's not going to seem right. That's not going to look like the point that's going to balance all these on a scale. Okay, so if I plot this point, 11/5 is a little bit bigger than 2, and then 3/5, that point would be right there. Okay, so yeah, that looks correct. That looks like a point that I would use to balance all 4 of these points on a scale. Okay. Now, what we're going to focus on. So this is just I talk about a one-dimensional system, a two-dimensional system here. Now, what if you want to look at a thin, flat plate of material of constant density rho called a planar lamina that occupies a region on the plane. Okay, we wish to locate the center of mass of the plate, which is called the centroid of the region. And just as before, you can think of it as the center of mass, x bar, y bar of a lamina as the balance point. Okay, so the point that would balance this point, if you were to put it on a scale. So figure 1 is kind of showing that. Okay, if the region lies between 2 curves, f and g, where f is the taller curve there, then the following formulas can be used. Okay, so to find the moment of the system about the x-axis, you're going to take rho divided by 2 times the integral going from a to b of f of x squared minus g of x squared dx. The moment of the system about the y-axis is where I take rho times the integral going from a to b of x times f of x minus g of x dx. The mass of the lamina, this plate here, is rho times the integral going from a to b of f of x minus g of x dx. Okay, the center of mass, or centroid, as we call it, has the coordinates x bar, y bar, where x bar is m sub y divided by the mass, and y bar is m sub x divided by the mass. Okay, so basically these 3 formulas are the 3 formulas to know going forward. Okay, you're going to be using those a lot. Okay, so when I was showing you this stuff up here, and on the previous page, this where you got a one-dimensional system, a two-dimensional system, and those are fine, but you're in a calculus class, right? So there's going to be integration type problems here. You're not going to be, multiplying and adding numbers, okay? So I've got some examples of where we're going to be finding centroids of regions here coming up. I've got 3 examples. Why don't we go ahead and stop the video right here, and I'll show you those in the next ones, okay?